Everyone, today we are going to conduct a video lecture series on simply structures. My name is Sachin Sandhi and I'm going to deliver a lecture on steel structures. So to design steel structure we need certain IS codes. So you should be able to have the copy of that so that you can design the industrial shed according to the Indian standard codes. So right now we require only four types of IS codes. First one is IS 800 2007 and other are IS 875 part 1, 2 and 3. And along with that you need a pen and a notebook and a calculator. So with the help of IS 800 2007 and IS 875 part 1, 2 and 3 we'll try to design the industrial shed. So we are going to use a limit state method of design for the design of industrial shed, and we are going to design that with the help of truss. So there will be a kind of a industrial shed where you can find a PV structure, pre-engineered building, but we are not going to design that. We are going to design only with the help of truss. So quotations are commonly printed as the means of inspiration and to invoke the philosophical thoughts from the reader. So in every lecture I'll try to give you one inspirational thought so that we can take inspiration from that particular thought. So today's inspirational thought is the first principle is that you must not fool yourself and you are the easiest person to fool, and this is the thought given by the Richard Feynman, the great physicist who has won the Nobel Prize. So next we'll start with the actual project. Now first we'll try to understand what is an industrial shed. So industrial shed is any building which is used in the industry to store the raw materials or to manufacture or to store the manufacturing products is known as industrial building. Industrial building may be categorized into two parts. First part is the normal building or normal industrial building, and the second one is the special type industrial building. So in the normal industrial type building you have two parts, or you have industrial shed type buildings with simple roof structures and open frames. So this is the structure that we are talking about, which is a very simple structure with all the open frames and it is having a truss on the top. And the special type of industrial buildings are buildings which are used for the other than the storage materials, which are used to manufacture heavy machines of production of power and steel mill buildings. So these are the special industrial type buildings, and this is the simple industrial building. So we are trying to design the normal type of industrial building in this particular course. So for this particular design we need certain requirements from the client. So as far as the today's lecture is concerned, we'll be assuming certain data so that we are going to using this particular data we'll be designing the industrial shed. So we are assuming that the truss is to be located in the Kolhapur region and the length of shed is 42 meter, span of shed is 12 meter, the column height is 10 meter, and the roofing material is AC sheet or the AC sheeting. You can have galvanized iron sheeting also. So depending upon the type of AC roofing material, will calculate the loadings accordingly. And the percentage of openings that are doors, windows, and ventilators that we are assuming here is 15%. So depending upon the percentage of openings or depending upon the area of the doors, windows, and ventilators, we'll be having the percentage of opening, which will help us to calculate the wind load. So the details of the truss that we have got from the site, it looks like something this. So it has got a 12-meter span which is on this, or you can see that in the elevation this is the 12-meter span on this side, and the length of the shade that we have already discussed is 42 meter along this particular side. So this is 42 meter and this is 12 meter, and the rise of this particular truss, which is this rise, is of 2 meter. So for this 42 meter length and for this 12 meter span and for this 2 meter rise we have this kind of a truss. The truss is spaced at a 6 meter distance, which is 6000 mm. So at an interval of 6 meter, you will find one truss of similar kind of configuration. So we'll try to design this particular truss, and we'll try to design the elements of the truss such as the rafters. So this is the rafter that you can see, which is indicated over here. Then these are the purlins that you can see. You can see these are the purlins which are there for the design. Then these dotted lines that you can see here are the sag rods. So you can see these are the dotted lines which are the sag rods, which will help us to which will help us to minimize the deflection of purlins. Similarly, we have these diagonal members which are called as diagonal sag rods, which will again help us to reduce the deformations of the purlin. So this is the overall configuration of the truss. Now this is the plan at the bottom chord level. So at the bottom chord level, you will have certain cross bracings to take the load because of the wind. So these are the cross bracings and these are the tie bracings. So you can see these are the tie bracings, and these four or these kind of bracings are the wind bracings provided at the bottom chord level or at the tie level. So you can see that this is the grid line for the truss. So 12 meter is the grid distance between the first column line and the second column line, and the along the length of the shed you can see there are number of column lines, so number of grids which are there, which will help us to identify the number of trusses. So considering this is the elevation of the truss, this is the elevation of the truss, which will help us to understand the girt and the bracings for the girt. So you can see that these horizontal members are called as the girts. So these horizontal members are the girts, and these vertical dotted lines and the inclined dotted lines are the bracings or the sag rods that you can see. So these are the sag rods, so which will again help to minimize the deflection of the girt. So considering this, you will have a minimum deflection value for the girt, and we have to design these bracings or the sag rods as well as the girts. So now what we are going to design this entire particular truss is the tension design or the tension member design, the compression member design, the laterally unsupported beam, laterally supported beam, laterally unsupported beam, and along with that the most critical part of our design is the wind calculations. So we'll be trying to calculate the winds according to the IS 875 part 3, and now it has been revised in 2015. Some of you might not be having this particular code, so try to download it and refer it, because it is slightly different from the earlier version, which has additional parameters that needs to be considered for the calculation of wind. So now what are the loads that will act on the truss? So the loads that will act on the truss can be divided into dead load, live load, and the wind load. So dead load, live load, and wind load, these are the three basic loads that we have to consider, we have to calculate to analyze the truss. So first we'll try to understand what is the calculation of dead load, and then we'll go upon live load and the wind load. So to calculate the dead load, we need to understand the configuration of the truss, and we need to calculate the wind dead load because of these parameters. So the self weight of the truss, then the sheeting material, which is the AC sheet material, then the purlin weight that we have to assume, then fixtures which are bolts, nuts, or the gusset plates, and services such as the plumbing connections if you want to provide, or the fan, or any other service provided material that it can be fixed to the truss has to be considered. So considering all these parameters, we'll try to calculate the dead load. Now I'll try to understand how to calculate the dead load. Okay, so first we'll try to calculate the dead load, and in the dead load the first one is the self weight. So self weight of the truss. So we have three basic different equations to calculate the truss. First one is the self-weight which is calculated when the live load is only up to 2 kilonewton per meter square. So if the live load is less than 2 kilonewton per meter square, we'll try to assume the self-weight using this particular formula, which is 20 plus 6.6 L. When the live load is more than 2 kilonewton per meter square, we have to multiply this particular formula with the actual value of live load divided by 2. So if the live load is 4 kilonewton per meter square, this will be 4 divided by 2. If the live load is 3 kilonewton per meter square, this will be 3 divided by 2. And if the truss is welded truss, then we have to refer this particular formula, which is 53.7 plus 0.53 A, and this is the Newton per meter square. This is Newton per meter square. So keep the units properly, because later on we are going to multiply this with the area. So this is for the welded truss. So now whatever we are designing, whatever truss that we are designing is, we are assuming that it is a bolted truss. So we'll be using the bolted truss equation assuming the live load is less than 2 kilonewton per meter square. So this is an assumption that we are doing, because generally for the industrial shed, the live load, maximum live load that you can expect is 1.5 kilonewton per meter square. So you cannot expect more than this, even though the industrial shed is a flat kind of a truss. Then considering this particular part, will be considering the live load less than 2 kilonewton per meter square. So you can see that imposed loads on roof. So you can see that imposed loads on various types of roofs, and where you can see the flat or sloping roof, curved roof with slopes including up to 10 degrees is 1.5 kilonewton per meter square, and on the sloping roofs with a slope greater than 10 degrees is 0.75 kilonewton per meter square when the access is provided. This is when the access is, you can see here, the access is provided, the maximum live load is 1.5 kilonewton per meter square. So there is no load which is more than this, so we are considering this. Now considering this, we'll try to calculate the self weight, which is 20 plus 6.6 into 12, and this is the span of the truss that we are having, which we have already seen in the earlier slides. You can go back to those slides. So you can see the span of the truss is 12 meters. So considering this 12 meter only, we are calculating the self weight. So L is the span of the truss, and area A is the area of one bay. One bay means area between the two column spacings. So you can see that if I want to calculate the area of one bay, this is 6 will be multiplied by the 12. So 12 into 6 will be the area of one bay. Now we'll go for the sheeting material calculation. So in the sheeting material, you can see that you have to refer to IS 875 part 1. So in the IS 875 part 1, you will find table number 1, and in that the point or the serial number 9 will help you to identify the, or help you to calculate the unit weight of AC sheet. So we'll go to that particular IS code and we'll try to understand. So IS 875 part 1, and here you can see the building materials are there. We will go to point 9. So you can see that there is asbestos cement sheeting, and there are three kinds of sheeting material that you might find, which is with a corrugated pitch, semi-corrugated and plain. So we are trying to assume the corrugated with 6 mm thickness, and the unit weight of that is varying between 0.1182 to 0.130, and the unit here is kilonewton per meter square. So 130 Newton or 0.130 kilonewton per meter square. So that is what we have done here. It is 130 Newton per meter square, which is the unit weight of the sheeting material. So now considering this, we'll try to calculate the area. on which the sheeting material is to be laid. So the sheeting material is to be laid on along the inclined length or the sloping side of the truss. So this is the inclined length that you need to calculate. We know the span is 12 meters, so half of that will be 6 meter. The rise is 2 meter. So based on that, we will be calculating the area allowed for the sheeting material, which is 2 into the inclined length and the spacing. This 2 is for the both sides. So this side it is 1 and this side it is 1. So it will be 2 into inclined length multiplied by the spacing. So it will be 2. This is using the Pythagoras theorem. You can calculate 6 square plus 2 square will be equals to inclined length, and this is the spacing, which is 6 meters. So considering that or calculating that, we have 75.84 meter square is the area, and the intensity of load on that particular area is 130 Newton per meter square. Now considering this, we'll go for the other parameters, which is fixtures that we are assuming is 25 Newton per meter square, service is 100 Newton per meter square, and purlins can be assumed between 70 to 125 Newton per meter square. For the industrial truss, we are assuming that as 70 Newton per meter square. So these are assumed values. You can vary this value up to 50, you can vary this value up to 150, and you can vary this value between 70 to 125. So this can be up to 50 and this can be up to 150. Now the next part is we have to calculate the total load. Now just now we have calculated only the area and the intensity. So now we have to calculate the total loads, and total load will be calculated considering the area multiplied by the intensity. Now the intensity of load for the self-weight, fixtures, services and purlins will act on the plane area. So this is the plane area of the truss. Plane area means the plan area. So where you can see that if this is the truss, this is the ridge line, or you can say this is the truss. So plan area will be the area of the or area that we are going to consider considering the plan of the truss. So this will be the plan, and at different intervals you have different trusses. So the plan area will be this spacing, which is 6 meter, and the span, which is 12 meter. So 2 into 6 is the 12 meter span, and this 6 is the spacing, considering that it is 12 meter per 12 meter square is the area. And for this particular area, these are the intensities of loads, dead loads of different fixtures or different materials is acting. So 72 multiplied by 99.20, which is the dead self weight of the truss, then 25 is the fixture, 100 is the service, and 70 is the purlin weight. Now multiplying this, you will get plus the area because of the sheeting material. So intensity of sheeting material that we have already seen is 130, and the area on which it is acting is 75.84. Now if I solve this, I'll get this value as 31041.60 Newton. Since these intensities are Newton per meter square and this area is meter square, so meter square gets cancelled, and the unit remains is Newton, and this divided by 10 to the power 3 will be giving you the value of dead load, which is 31.04 kilonewton. So the final value for the dead load is 31.04 kilonewton. So in the next lecture, we'll try to calculate the live load and the wind load. Thank you.